order to try to understand some of the different techniques that can be used in this field, in electrophysiology. Today's activity is intended to be as a short introduction to electrophysiology, just to give some basic concepts in order to navigate through the future events. We will have a webinar next week from Dr. Alessandro Maccione from the Italian Institute of Technology. He will speak about a new emerging technology, which is the high-density multi-electrode array technology. And in particular, it might be interesting for some of you because he will speak how to use this technology, especially in cell cultures. Then, the week after, we will have a data club in which Matteo Di Paolo and Serena Riccitelli will tell us how they've been collecting their data during their project, how they've been analyzing this data, and they've been collecting data using a different technique, the electroretinographic recording. And finally, we will have, on the 2nd of March, we will have a seminar from Professor Silvia Bisti that, as you know, she's been a professor of this department of physiology, and she just retired at the end of October last year. And actually, she achieved many findings in this field, and therefore she will be surely a beautiful summary of the month. Okay, so obviously we need to start the introduction with a sort of definition. So we can define electrophysiology as a branch of physiology that deals with the electrical activity that is generated by living organisms. Now, I'm a bit weird person, and every time I speak about electrical activity and living organisms, I immediately start to think about a book, Mary Shelley's book, where Dr. Frankenstein was able to give life to this monster just by injecting electricity in his body. Now, we all know that is actually impossible, and we also know that the electrical wires that are in the walls of this room are not living organisms. So this sentence is not really correct, but if we turn this sentence upside down, we come up with something that it's more truth. So life is electricity. For example, in fact, if you want to define legally a man dead or alive, what we have to do is to perform an electroencephalographic recording and to record the electrical activity that the brain of this man is able to generate. When we can record electrical activity, this man is alive. When there is no more electrical activity, unfortunately, this man is dead. Now, what I'm trying to say is that only living organisms can perform electrical activity. Dead organisms cannot. So, and the reason for this is the fact that we need to spend energy in order to have electrical activity. Now, to try to elucidate this concept, I thought to a bit weird example. Let's imagine to have an hydroelectric power plant. In a hydroelectric power plant, what we have is a lake, a dam, and then a valley with a river. Now, as soon as we open a conductance in the dam, what happens is that the water will spontaneously flow from the lake down to the valley. And we can use this flow of water to produce electricity. For example, we place a turbine in this water, and this turbine is connected to a sinusoid that is rotating in a magnetic field, and therefore we obtain electricity. Using the same forces, we could also produce different things. For example, if instead of the sinusoid, we place some stones, and instead of the magnetic field, we place some olives, we could obtain olive oil. Okay? So by using the same energy, we could obtain different products, different things. Now, to have a power plant that is economically sustainable, usually we build these plants in a place where there is a river that continuously fill up this lake. Okay? But unfortunately, cells do not have this opportunity. So what the cells needs continuously to do is to pump, let's say now, the water from the valley back to the lake. And to do this, therefore, they need to spend energy. Okay? Let's try now to take this weird example a bit more to reality. Here we have 3 different cells coming from the 3 different living organisms. the squid, and a neuron from the squid, a muscle of the frog, and a neuron of a mammal. Now, what we can see is that here are represented the extracellular concentration and the intracellular concentration of each ion. And here, from this concentration, we will see a bit later, we can calculate the electrochemical equilibrium potential of that ion, which means that at this potential, that ion will be both in the electrical equilibrium and in a chemical equilibrium. Okay? So once is reached that potential, we have no more movement of ions. What I want you to notice is that the resting potential of the membrane of these different cells instead is always far from the equilibrium potential. So what the cell is doing is to have always a difference, so a sort of driving force here, because these two potentials are always different. So what happens is that every time that the membrane, that the cell decides to open a channel, an ion channel, the ion channel will spontaneously flow through the membrane, as we have seen, like the water was doing in the hydroelectric power plant, because of this difference of potential. Okay, this is the driving force actually that allows our ions to move through the membrane. Now, why is this? Because at the resting potential, the sum of all the current that is passing through the membrane is equal to 0, and therefore we are in a state of electrical equilibrium, but we are not at the chemical equilibrium. And therefore, cells need to continuously spend energy in order to keep this disequilibrium, this chemical disequilibrium. Okay? And this chemical disequilibrium allows the spontaneous flow of ions through the membrane. Now, let's think, for example, what happens in a neuron on a different cell when it decides to open a calcium channel, for example. Some calcium will get into the cell, and for example, the frog muscle will start a contraction. Or calcium could, in neurons, activate really an enormous various pathways that will lead to different destinies, to different fates. So it's obvious that we can use this potential energy that we are accumulating by keeping the resting potential far from the electrochemical equilibrium to do different things. Moreover, if whenever an ion is flowing through the membrane, what happens is not only that we have generated a current through the membrane, but also that we are changing the membrane potential. And we know that cells communicate by changing their membrane potential, for example, by performing action potentials. So we spend a bit of energy, but then we can produce many different effects. To try to formalize a bit more this concept, I want to recall you that the equilibrium potential can be predicted by using Nernst equation. And what I want you to notice is the fact that Nernst equation is telling us that the electrochemical equilibrium depends exclusively from the different concentration of that ion through the membrane. Okay? If instead we want to model membrane potential, so the resting potential, which would refer to a different equation, which is the Goldman-Hodgkin-Katz equation, in which there are some differences, as you can see from Nernst equation. The first difference is that now we are considering all the different ions that are present in the solution where the cell is living, and not only a single ion like in Nernst equation. The second main, something similar is the fact that we observe here the same variable as in Nernst equation, so we take in consideration the different concentration of that ion through the membrane, but we have a new variable here. We have the permeability variable. This term tells us that how easy for an ion to get through a membrane, a cellular membrane. Okay, so the permeability is measuring this, the easiness for a particle to pass through the membrane. I don't know if it's correct that term or I invented it. Anyway, but what this equation is telling us, therefore, is that, again, every time we change the permeability of the membrane for some ion, the effect will be to change also the potential of that membrane. Okay, V is changing. And finally, we have a very important law from physics, from electrical circuits, the Ohm's law, that recalls a bit this concept. In fact, we know that a current that is passing through a resistor will produce a drop in the voltage of that circuit. Therefore, if we think again to our biological example, when an ion is passing through a channel, we have a current, I. The channel can be considered as a resistor, R, and every time this current is flowing through the membrane, we change the membrane potential, so V. So V is equal R for Ohm's law. Okay? Now, so we should have understood approximately why we spend energy to obtain a potential energy that we can use for different things. And now we should be more interested in trying to record this electrical activity. So let's try to see how we can do it. Now, as soon as we try to solve the problem of how we record an electrical activity from a living organism, we immediately face up the scale problem, which is a problem that is actually happens for every field, every scientific field. This problem is telling us that it's not very smart to use this incredible gun to try to kill an annoying fly. And it's not even smart to use this sort of weapon if we want to kill Hulk Hogan. Okay? What I'm trying to say is that you have always to use the right technique to answer to your question. There will be never a single technique that is able to answer to every question. Every technique has some good things and some drawbacks. Okay, we will try to see what are the good things and drawbacks of bit different techniques here. Now, one thing that is quite handy is the fact that in electrophysiology we always use approximately the same kind of weapons, let's say. So we always use an active electrode, and then we use a reference electrode. And what we want to do is to observe the differences in potentials that are developing between these two electrodes. Okay, so what we are doing actually is to close an electrical circuit between our living organism. So, and this is actually very important to understand because this means that all the currents that are generated by the living organism should flow through my circuit, and this is actually the current that I'm going to measure, or the difference in potential that I'm going to measure. Okay? I can do it because I can close a circuit with a living organism, an electrical circuit. Okay, and now we come to a quite important concept from my point of view. I'm joking, but that is, it's not only important to have an active electrode, but it's also important to know where you're placing your electrode. Okay, this is something that is also useful in life, but in electrophysiology is very important. Now, here in this slide, we summarize a bit all the possible different techniques. We can observe two different domains: the extracellular domain and the intracellular domain, and we have different techniques that can be used in these two different domains. Now, for what concerns the extracellular domain, we can use the extracellular recordings or the planar multi-electrode array or microelectrode array. While for the intracellular domain, we can use patch clamp technique and the intracellular recordings. Now, I was saying that it's very important where we are going to place our electrode, because it will have obviously consequences on the signal that you are recording and on what we are recording. In fact, for example, if we are interested, for example, in record what is the spiking activity of a neuron in response to a certain stimulus, what we should look for is an extracellular technique, for example, because extracellular technique allow to record the spikes, so action potential from a neuron, do not perturbate anything inside the cell, and moreover, with a single electrode we could record tens or even more neurons simultaneously in the same time. So just imagine we place an electrode in the brain, and we could record the activity of different neurons just in a single time. Obviously, this is not possible in the intracellular domain, where we are forced to record a single cell per experiment. Okay? But obviously, the good that is to record different neurons in just a single time. Actually, sorry. The main difference between the extracellular recording, which is performed with an electrode, and the planar microelectrode array is actually that in the planar microelectrode array, the shape of the electrode is different, so it's not that pointy electrode, but it's just a planar electrode. But the main difference is that the fact in the microelectrode array we have an enormous number of electrons. Okay, for example, in the high-density microelectrode array that we will see next week, we have 4,096 electrodes. And this means that we can record from thousands of cells simultaneously in the same time. So, for example, we could have a dish with different cell cultures, and we could record the neuronal activity of those cells simultaneously in just one time. But, as I was saying, these are the advantage, many cells in a single time, but there are obviously some drawbacks for this. Now, the first drawback is that the shape of the signal that we are recording is completely different. Now, to try to understand this, I ask you to try to think as an electron. Okay, so what I'm doing is to place you now inside the cell. Okay, so you are now inside the cell, and this neuron is now creating an action potential. What you should see, therefore, is that some sodium will immediately get toward you, because the sodium is getting, during the rising phase of the action potential, you know, the sodium is getting into the cell. Okay, so these are positive charges that are moving toward me, and therefore I'm getting more positive. And in fact, when I'm inside the cell, in the intracellular recording, what I can see is that my trace is going up. In the hyperpolarizing phase of an action potential, what we will see if we were inside the cell would be that the potassium is now flowing outside of the cell, so it's moving away from me. So positive charges are moving away from me, and therefore I'm getting more negative. Okay, so I hyperpolarize. When my electrode instead is outside, and so now we move outside of the cell, what we will see is, firstly, the sodium that gets into the cell, so now the sodium is moving away from me, okay, from my electrode. And this is, so my electrode is becoming more negative. And this is the reason why we start to see this drop in potential there. Then we would see a potassium that is coming out of the cell. And so a positive charge moving toward me. So I'm getting more positive, and what I record is now a positive signal. So it's obvious that the shape of the signal is completely different. We have a monophasic signal up in the intracellular recording, a biphasic or even a triphasic signal in extracellular recordings. And I want to point out also that the amount of information that we can get from the signal we have recorded is also completely different. In fact, in the intracellular recording, we are speaking about millivolts. Okay, so a nice big signal, and we can really analyze this signal in different things. For example, with an intracellular recording like this, we could understand what is the level at which what is the trigger level that triggers the action potential, for example. With a recording, with an extracellular recording, the only thing that we can really do is to record that there has been an action potential, but we cannot really say anything more about that action potential because the information is much lower. We are now in the microvolt range. Okay, so a much smaller signal and a completely different signal. So we cannot tell a lot about the intracellular properties of that cell, but we can say that this cell has fired an action potential. And this, for some question, may be already a lot. Now, it's also sometimes helpful to think to the electrode as a sort of a microphone. If you place a microphone in front of my mouth, you will record my voice very clean and very loud. Okay? Obviously, if we start to move this microphone away from me, you would record a voice that is much, it's bad, I don't know how to say it, to define the quality of sound in English, I'm sorry.
It's a bit noisy.
But,
Noisy.
Noisy. You see the mathematical guy always with noise immediately. So what I'm trying to say is that the signal that you are recording depends from the position of your electron. Okay, so this is another thing that we have to consider when we are in the extracellular domain. So the spike that we are recording, as you can see in this example, has always a different shape, whether we have recorded it with an electrode placed here or close to the soma. Now, the action potential, you know, is always the same, but it's just how we are sensing this action potential. Now, this might look like a drawback, but sometimes instead it's very, very useful for a scientist, and Flora could tell us, and Anna Maria also a lot about these kind of recordings. Because, for example, I told you that with an extracellular electrode, you could get spikes from different neurons. Now, obviously, neurons are not always in the same location, so they usually are in different locations. And therefore, the spike that is generated by one neuron will arrive to my electrode with a different shape and a different amplitude than the spike generated by another neuron, for example. And by using, for example, an analytical method that you could explain to us much better, and therefore I will not explain. For example, by using principal component analysis, we could try to sort these spikes and so to attribute a spike signature to some cell. So we have seen something about extracellular recordings. Let's move a bit more in the intracellular domain, which is the domain where I usually work. Now, the main difference between intracellular and the patch clamp recording is the fact that with the intracellular recording, you can record well the membrane potential fluctuations, but you cannot record, for example, the currents that are generated in a synapse, or the currents generated because some channel is open. I was just thinking, for example, now I saw you, Vimal, sorry. For example, on Tuesday, Vimal has given a very nice seminar, and he was speaking about lipocalin 2 and his role in the iron movement through the membrane. For example, also that current, we might be interested in looking at that current, and therefore, what we should use is an intracellular technique, and we should use patch clamp because we want to look into a very tiny current. Now, the main difference, in fact, between these two techniques is in the way we put in communication our active electrode with the intracellular side of the cell. In fact, in the intracellular method, what we do is to take the electrode and just a bit roughly place it into the cell. But by doing this, obviously, we create a quite large hole in the membrane. Okay, that is not completely filled by the tip of my electrode. And therefore, obviously, through this hole here, lots of ion could pass through. Let's imagine just, for example, calcium will start to get inside the cell and will probably start to kill the cell, for example, after a few minutes. So usually intracellular recordings like this are performed just in very large neurons. In fact, it was used for squid giant axon neurons. But if we want to analyze a smaller cell, or we want to be really precise, we need to use the patch clamp. With the patch clamp technique, we really take a lot of care in opening the hole through the membrane of the cell, and therefore what we do is to produce a hole without any leakage, okay, here. And this is very important because we want to see a very small current passing through the membrane, and therefore we do not want any currents that gets our signal noise. So how can we do this? Well, we need to use obviously a particular electrode. Now the electrodes usually are wires made of silver chloride, and the silver chloride is the chloride of this silver chloride. The wire is in equilibrium with the chloride of the solution with which is in contact. So, since we are speaking about dimensions, very, very small dimensions, this pipette here, this is a glass pipette, actually this thing here, is a borosilicate glass that we need to pull every day just before to perform the experiment, because the tip of this pipette needs to be very, very small, like 1 micron diameter, and therefore some dust could already clog this pipette. So you have to produce it and then immediately go for a recording. So inside this pipette is filled with a solution that is called intracellular solution, and mimics perfectly, at least what we can do, the intracellular milieu of a cell. Okay? So for example, inside here we place potassium chloride, for example, usually, because we know potassium usually in cells is a lot. And we will place some ATP, some GTP, just to give to make the cell a bit more happy. And now what we need to do is to approach the cell by using a micromanipulator, because obviously we need to perform all very small movements. Now, since we are dealing with very, very small distances, it's impossible to measure by distance the contact that I'm performing with the cell membrane. So we use a different concept. We use the resistance as a measurement of distance. I will try to explain you how. So we have an electrical wire, we have an active electron here, and then we have a ground that is somewhere here in the bath. So the circuit is closed in this way. So current, if I impose a voltage squared pulse into my active electrode, what I will generate is a squared current that will move from my active electrode to the ground that is placed somewhere in the bath. Okay. Now, obviously, this current needs to pass through the pipette. Okay, and we told that the pipette is very, very small, and therefore the pipette will oppose some resistance to this flow of current. Okay, so this means that when we apply a known voltage pulse of a pulse of voltage, what we can record is a pulse of current, and the dimension, the amplitude of this pulse of current, obviously will be proportional to the resistance of my pipette. Always because of the Ohm's law, V is equal IR, so we can get R. Okay, easily. We know V and we know I now. Now, what happens? And so, by measuring this resistance, we can get information about how large is the pipette. Okay, smaller resistance means that the tip is large. A high resistance means that the tip is very small, because there is more resistance for the current to get to the ground electron. Now, let's move toward the cell. What happens as soon as we approach the cell membrane is that the membrane will start to clog the tip of my pipette, and therefore what happens is that the resistance will suddenly increase a lot, because less current will be able to flow through my pipette, out of my pipette. And therefore, and this is depicted here, we have the same voltage step applied here, but now, as you can see, the current that we can record is much smaller, because resistance has increased a lot. Okay? So, what we do, this is an animated GIF, so we will repeat. So what we do is to monitor